In this video we will explain the PRACH counters and KPIs, followed by a troubleshooting process, which will explain all parameters involved in each step during the PRACH procedure. Once the eNode B receive message 1 from a UE, random access preamble message. The eNode B increments by 1. The LTE random access group A. Attempt counter, if the random access preamble is sent in group A. The LTE random access group B, attempt counter, if the random access preamble is sent in group B. The LTE random access dedicated attempt counter, if the random access preamble is a non-contention based. The LTE random access dedicated for handover attempt counter, if the random access preamble is a non-contention based sent for a handover. By sending message 2, random access response to the UE. The eNode B increments the following counters based on the received random access preamble type. LTE random access group A. Response. LTE random access group B. Response counter. LTE random access dedicated response. LTE random access dedicated for handover response counter. After receiving random access response message, the UE send RRC connection request message to the eNode B with RRC cause, which can be for signaling or data. Then the eNode B increments the following counters by 1. The LTE RRC connection request attempt. LTE random access dedicated message 3 reception for non-contention based. And LTE random access dedicated handover message 3 reception for handover procedure. In the next step, the eNode B send to UE the RRC connection setup message with contention resolution that indicate a successful random access procedure. The following counters are incremented by 1. LTE random access group A, contention resolution. And LTE random access group B, contention resolution. The random access setup success rate is divided into contention-based and non-contention-based. The random access procedure is successful for the contention-based when the eNode B send message 4 with contention resolution indication. And for the non-contention-based is successful when the eNode B receive message 3, then the contention is resolved. Based on the random access KPIs, if there is any degradation in the KPI trend, the troubleshooting process is as follows. Troubleshooting of random access procedures. First check, is the random access preamble is received by the eNode B? Second check, is the random access response received by the UE? Third check, is the RRC connection request message received by the eNode B? Fourth check, is the RRC connection setup message received by the UE? There are 4 steps that shall be troubleshooted based on KPIs, and the attempt volume for each signaling message. The UE receive the random access parameters in System Information Block Type 2, which contain the preamble setting, the number of preamble for random access contention based, available in the cell, the number of preamble in Group A, the message size of Group A, the power offset for message within preamble Group B, the message 1, power setting that indicate the ramping power for the preamble retransmission and the initial preamble power target. Also System Information Block Type 2 contain the parameters to supervise the PRACH procedures, the maximum number of preamble transmission, the random access response window size, the contention resolution timer, the maximum acknowledge for message 3 retransmission. The System Information Block Type 2 include also the physical PRACH configuration and preamble generation parameters, the route sequence index, PRACH config index, the high-speed flag indicator, zero correlation zone configuration, and PRACH frequency offset. The UE generate the available preamble based on route sequence index, zero correlation zone configuration and the high-speed flag parameters. And choose randomly a preamble from the generated list, and send it to the eNode B. The preamble power used to send message 1 is set using open-loop power control. In this case the UE cannot adjust his power based on the current RF conditions, for example weak signal level, or high uplink interference. The PRACH power is defined by the following formula. Minimum of PC max, and P0 pre, plus PL, plus delta preamble, plus N pre, minus 1, multiplied by delta step. Where PC max is the max UE power capability 23 dBm. P0 pre is the preamble initial received target power parameter, range from -80 to -130 dBm. PL is the measured path loss by the UE. Delta preamble is 0 decibels for preamble format 0 and 1. The following table define the value of delta preamble for each preamble format. N pre is the maximum UE preamble retransmission, defined by preamble transmax parameter. Delta step is the power ramping step for preamble retransmission, defined by power ramping step parameter. The message 1 power parameters are transmitted in System Information Block Type 2, power ramping step, preamble initial received target power, and preamble max transmission. The first preamble is transmitted without power ramping as the N pre is equal to 1. If no response is received within random access response window, the power is adjusted by the power ramping step, and preamble gets sent again. The random access response window starts at the last subframe containing the end of the previous preamble, plus 3 subframes, and ends at the last subframe containing the end of the previous preamble plus 3 plus response window size. If there is no random access response received by the time preamble transmission max has been reached, the random access process will be stopped and higher layers will be informed. The value of the random access response window size is received in System Information Block Type 2. The power level can cause the no receiving of message 1 by eNode B, that can be adjusted by power ramping and preamble initial received target power parameters. The second cause of message 1 failure is preamble collision, which can be caused due to few number of preamble in the cell. In the next slide we will explain how to optimize the preamble collision. The available 64 preambles in a cell are divided into preamble for contention-based and dedicated preamble. The ratio is defined by the random preamble ratio parameter. If the collision probability is high, the random preamble ratio can be defined using the ratio of the counters, LTE random access group A attempt plus LTE random access group B attempt, divided by LTE random access dedicated attempt counter. The preamble for contention-based are divided into Group A and Group B. Then the ratio of contention-based Group A and Group B can be calculated based on the ratio of LTE random access Group A attempt to LTE random access Group B attempt. The message size Group A parameter can be adjusted to decrease or increase the opportunity to select a preamble from Group A or B. In the next slides I will explain the preamble conflict issue and how to identify and detect a conflict between two cells. When two cells use the same PRACH route sequence index, the probability of false alarms or preamble collisions increases. When the UE send a preamble to cell A, the cell B also detect the preamble sent by the UE. In this case the preamble is a false alarm for cell B. This scenario increased the collision probability when two UEs use the same preamble under two different cells. The PRACH route sequence index conflict detection feature enables the eNode B to detect route sequence conflicts between the serving cell and intra-eNode B or intra-eNode B neighboring, by selecting the eNode B algo switch route sequence conflict detection switch parameter. The preamble collision impact also the random access performance, to calculate the preamble collision probability. UE Random Access Information Inquiry enables the eNodeB to send UE information request messages to UEs that allow the UEs to report their random access information. The UE Random Access Information Query feature can be enabled by switching on the UE Random Access Information Inquiry switch option under the cell Algo Switch PRACH Algo Switch parameter. This function is recommended when more than 80% of the UEs in a cell comply with 3GPP Release 9 or later and supports RACH information reporting. By receiving the UE information response, the eNodeB increment the following counters by 1. LTE Random Access UE Information Response Number contain RACH information. LTE Random Access UE Random Access Information Response messages whose contention detected is true. Then the preamble probability collision is given by the ration of LTE Random Access UE Random Access Information Response messages whose contention detected is true. 2. LTE Random Access UE Information Response Number contain RACH information. The probability of falsely detecting preambles is given by the following formula. All preceding settings and parameters are related to random access message 1 optimization. The next step is to optimize the message 2. Optimization of message 2, random access response. The UE initiate a random access procedure by sending a RACH preamble to eNodeB. If the preamble is correctly received, the eNodeB acknowledges it by sending a random access response message, message 2. The message sent over the physical downlink control channel PDCCH is actually a pointer via RARNTI to the actual resource in the physical downlink shared channel PDSCH, where the random access response can be received. When the eNodeB receives the preamble and sends a random access response, the UE may not be able to receive the random access response due to downlink interference or bad RF conditions. The random access response message is scheduled on PDCCH. Its aggregation level can be adjusted by the parameter cell PDCCH Algo Common Signaling Aggregation Level. Default value 4. The PDSCH message for random access response is sent using QPSK modulation and coding rate is set by the parameter cell downlink scheduling algo random access response and paging code rate. Default value 0.117. The power level of random access response message can be adjusted by the random access response power parameter under cell channel power configuration. The PDSCH configuration reference signal power is the cell RS power. If the random access response message is used for a handover procedure, the power level of message 2 can be adjusted by selecting handover random access response power enhanced switch under cell channel power configuration. Then, the power of message 2 is defined by the following formula: the reference signal power plus random access response power. N is the number of message 2 transmission. If n equal to 0, the first transmission, the power level is the RS power plus random access response power. If n equal to 1, the second transmission of message 2, the power is the RS power plus random access response power plus 3 decibels. If n equal or greater than 2, the number of retransmission is more than 2. The power level of message 2 for a handover procedure is the RS power plus random access response power plus 6 decibels. The PDCCH aggregation level of message 2 can be optimized by selecting handover success rate boost optimization switch under handover signaling optimization switch that allow the eNodeB to change the PDCCH aggregation level to value 8 when n random access response message for a handover is retransmitted. In the coming slides, we will troubleshoot the parameters impacting message 3. The UE initiates the RRC connection establishment procedure when upper layers request establishment of an RRC connection, while the UE is in RRC idle state. UEL3 sends RRC connection request to lower layers Layer 2 and Layer 1, which are responsible for preamble sending and random access response monitoring, and starts timer T300 which supervises the RRC connection establishment procedure. The timer start when the transmit RRC connection request, and will stop when the UE receive an RRC connection setup, or RRC connection reject message, or cell reselection, and upon abortion of connection establishment by upper layers. In case of UE timer T300 expiry, the UE will stop RRC connection establishment procedure and informs higher layer about failed procedure. By sending the RRC connection request message, the UE starts also the contention resolution timer. The maximum content resolution timer parameter defines the maximum amount of time allowed for contention resolution. The value is defined by random access channel configuration contention resolution timer. The timer starts when message 3 has been transmitted and restart when UE receive a HARQ feedback. The timer will be stopped if the UE does not receive either message until the timer expiration. By expiration of contention resolution timer, the UE resend a new preamble again for random access procedure. When the UE starts contention resolution timer, if a NAC is received from the E node B, the UE retransmits again the RRC connection request message. The number of retransmissions for message 3 can be adjusted by the max HARQ message 3 transmission under random access channel configuration. If the message 3 is for a handover procedure, the max number of retransmission is defined by uplink HARQ max transmission number under cell uplink scheduling algo. In System Information Block Type 2, the UE receive the T300 timer, the contention resolution timer, and the max HARQ for message 3 retransmission. For the message 3 in handover procedure, the max number of uplink HARQ transmission is received in RRC connection reconfiguration message under radio resources configuration dedicated setting for UE. The power of message 3 is based on the power of the last transmitted random access preamble, the one which UE received random access response for, plus 2 adjustable settings that can be used for offsetting the power. The PUSCH carrying message 3 uses open loop power control. Delta message 3 is the fixed power offset of message 3 relative to message 1. This offset is specified by delta preamble message 3 under the cell uplink power control common parameter. Delta message 2 is the power offset used to calculate the message 3 power during uplink random access. This variable is also used to specify the initial power of the PUSCH or PUCCH for closed loop power control. This variable is specified by delta message 2 under cell uplink power control common parameter. The UE receive the delta preamble message 3 parameter value in System Information Block Type 2. And delta preamble message 2 is indicated by the E node B in random access response message in TPC. Transmit power command, related to random access message 3 or first scheduled uplink transmission. The power of message 3 can be adjusted by delta TF and a closed power control part defined by FI. Delta TF is the PUSCH transport format depend on MCS. And F is the transmit power increase for the random access plus delta preamble message 2. Delta TF is defined as following: 10 log of 2 exponential of MPRI multiplied by KS minus 1, where KS equal to 1.25 and equal to 0 when KS equal to 0. The KS value is defined by the parameter delta MCS enabled under cell uplink power control dedicated. The KS equal to 1.25 when delta MCS enabled is set to UU enable, and 0 when UU disable. MPRI is the number of TBS divided by number of resource element, which is the number of bits transmitted per resource element. FI is the PUSCH transmit power adjustment value for the UE, mapped to the TPC command sent over the PDCCH. Where delta PUSCH is a UE-specific correction value, also referred to as a transmit power command, and is included in PDCCH in the downlink. Delta PUSCH I-4 indicates correction signaled on PDCCH in subframe I-4. Delta PUSCH equal to 0 decibels for a subframe where no TPC command is decoded or where DRX occurs. The delta PUSCH is accumulated values signaled on PDCCH with DCI format 0. The values range are -1, 0, 1, and 3. The delta PUSCH accumulated values signaled on PDCCH with DCI format 3 and 3A are one of the values -1 and 1 or -1, 0, 1, and 3, as the values are semi-statically configured by higher layers. The value of F0 is equal to delta power ramp up plus delta message 2. Delta power ramp up is the transmit power increase for the random access. Delta preamble message 2 is the offset used for power calculation specified by cell uplink power control common delta message 2. Once the RRC connection request message is transmitted successfully, the UE monitors the PDCCH to locate where the message for will be scheduled. The PDCCH aggregation level for SRBs can be adjusted by the PDCCH initial CCE adjust value under cell PDCCH algo parameter.